Very much, Victor. Right, my name is Andrey Kiselev, and it's my pleasure to be here. Thank you very much for this opportunity. So for the next hour, we're going to talk about assistive robotics as it's the topic for today, and we'll take a look at it in the context of elderly care, basically from concept development to commercialization. This is an overview presentation, so we are not going to go deep into details of all the works that are mentioned in the presentation. So if you're interested, please reach out to me. After that, I'll give you all details and contact to the people who are behind those works. Right, so I have to say, this is a brand new presentation, freshly done. I have no idea how much time it's going to take. We'll try to stick to the schedule, 45-50 minutes. In the best case, we'll have a little bit more time for discussions. We'll see how it goes. And now I have to figure out how to switch slides. I hope this works. Right. So there are basically a couple of things I wanted to talk about. And I'll start with setting up a little bit of frames. What do we mean when we say assistive robotics? And you had a lot of presentations today, wonderful talks on the topic. I'll not repeat what has been already said, just say I will just set some frames in which we work. We'll take a look at the project spectrum, how works on assistive robotics are implemented, and in research work on European scale, and most of the works are on European scale. And then we'll have some historical pieces, blast from the past or from the present or from the future, basically some particular examples of works. And the focus, what I want to do today is to look at the methodology. What is the approach to address the problem, to attack the problem of developing efficient or good assistive robots? So what is that thing that we believe is going to be good for society and good for healthcare or elderly care? So as Victor said, I come from Örebro University, Center for Applied Autonomous Sensor System. To give you a little bit of a background, I had to put a big dot here, otherwise you'll never find Örebro on the map. We are located basically halfway between Stockholm and Gothenburg. Anastasia said just before lunch that it's very hot in Stockholm. Fortunately, it's quite chill now in Örebro. It's about 27 degrees, down from over 30 a couple of days ago, so we're quite happy still. We keep windows closed so there are no noises. Örebro is a fairly small city, but Örebro University is fairly big for the city of our size. We have 15,000 students, about 500 PhDs in different programs, a little less than 1,000 teachers and researchers, and 140 professors. And we have schools in all major topics. We have, for example, well, Örebro University Hospital is a part of university. We have School of Culinary Arts, we have School of Music, and we have the School of Natural Science and Technology, where I come from. And we are number 75 in Times Higher Education ranking among young universities. That is very good result, considering that we are a university basically a little more than 20 years. And what is ASS? We are a research center. We are about 60 to 70 researchers. We're growing from all continents on the planet excepting Antarctica. It's hard to hire people from there. More than 20, I think we're approaching 30 PhD students, 7 professors. And what we do is AI and robotics. So we make robots smart. We make robots go straight line. That is sometimes a challenge. We make them smart. We make them perceive the world around us. We make robots reason, and we make robots act. And our big application domains are healthcare robotics and industrial robotics. And in healthcare, we look a lot at elderly care domain. So why is assistive robotics? Why is it interesting? And there is a lot of reasoning. Why is it important, right? So I have 3 points here in the slide. There are many studies that show that you can reduce rehabilitation time, for instance, when you apply assistive robotics in rehab scenario. There is improved quality of life for elderly people, for instance. There are studies showing that. If you take a look at any European proposal, in 9 cases out of 10, you'll find the first sentence saying, oh, there's a aging European population and that needs to be supported. That is all important. We all know that. There's no way we progress as a European society without investing into technology to assist us. But what do we actually mean, and why is it interesting to work on assistive robotics as a researcher? So what we mean by saying we have assistive robot is, first of all, embodied system. And Guillem made a very good point in the morning. He mentioned that embodiment is very important. There are many studies showing them, for instance, by Maya method, showing that embodiment is a vital part. Embodiment improves interaction. So we work on embodied systems. And here on the right, you have some, on the right part of slide, we'll have some examples of, they come from the robot called Robotera. And the purpose of that project was to combine different robotic technologies, different assistive robots working in different environments to work as the same system. So a person might have a robot at home, and that robot has some communication features and some robotic arm to help out that robot. And then there is another robot that can help you to go groceries. And all those things will work together, but each of them independently is an assistive robot. Then a vital feature is that this device, whatever we call it, assistive robot or some platform, it has to do perception, reason, and act, right? So this loop has to be fulfilled within this embodied system. It has to perceive environment. Well, it has to sense the environment, right, with sensors, whatever they are. It has to perceive and understand what is that environment, what is my place in that environment. It has to also have proprioception, right? So what is my position in this environment, doing some basic SLAM. It has to do reasoning. It has to have some understanding of what do I need to do at each moment of time, or what should I not do. And then it should be able to act. So it has to be able to move, or it has to be able to reach something, it has to be able to manipulate somehow. And the most important is that in assistive robotics, we say that it compensates for loss of function. So if we think about a robot, some robots that assist, one humans to combat other humans on the battlefield, that is not assistive robotics. In assistive robotics, we help people who have loss of function for one reason or another. It could be illness, it could be natural decline, it could be something that limits, that causes the loss of function. And that sparks by itself a bunch of ethical questions. So loss in comparison to what? Can we talk about some average human being? Can we talk about some natural flow of aging? And that is a very interesting question. And here we have a lot of intersection with other fields. So of course we work in robotics, right? But we also take a look a lot at questions in gerontology. What is the normal aging flow, for instance, of aging population? And one of the interesting aspects that make this topic particularly interesting to me is a combination of social and physical assistance. If you look at those robots on the image on the right, there's a reason I bring it here, is that pretty much all assistive robots that we place in human homes or in some rehab facilities or in some elderly care homes, most of them combine social interaction with physical assistance. So most of them have some sort of manipulators to help you out with something. They can at least I can maybe run around and say, oh, you've forgotten your glasses in the kitchen. And they have a bit of social interaction, so they can social assist the person who is maybe experiencing lack of social contact, which is the case of with many elderly, unfortunately. So one particular technology we've been focusing for many years is called mobile robotic telepresence. I think most of you know what it is. I'll just make a brief overview. So you can say mobile robotic telepresence as basically, I don't know, Skype on wheels, some communication technology combined with mobility. And it can come in different forms. It's not necessary that MRP system is an independent robot. On the right side here, I have the blue one. It's called Giraffe, and it is an independent MRP system. So basically, screen, computer, and wheels. It's nothing more it can do. You drive it around, and you can talk to people who are located with the robot. But it can also come as an independent, as a part of another robot, like Pepper. So if you have seen Pepper, right, it's humanoid robot that has tablet on the chest, and that tablet can work as a communication device. So why is it interesting? Because you have a bunch of interaction in the same system. In telepresence, the whole point of doing telepresence is to have human-human interaction, right? So you have human on the left and human on the right, and they're supposed to talk to each other. And in case of ideal mobile robotic telepresence, the communication channel should be transparent. So normally, in a very idealistic case, which is not existing in practice, you shouldn't notice that you have a communication channel between you, pretty much like Star Wars holograms, right? In reality, you have a bunch of other interactions that come in play. And if we go from left to right, so you have interaction between remote user, and remote is the one who is connecting from some remote location. So it's communication of that user with some kind of interface, could be computer, could be tablet, phone, whatever can connect to your robot. Then there is communication between robot and the local user. And that can come in different form. It could be physical HRI, it could be something else. And depending on what is that robot, there could be small or big aspect of human agent interaction. And if we look again at Giraffe and Pepper on the right side, when I've seen Giraffe first time, my first idea was, oh, what kind of rubbish is that? It's not even a robot. And when we started experimenting with that, we found that it's actually a quite interesting device because it doesn't really have its own personality. It doesn't postulate itself as something intelligent, right? So there is always human inside, connecting remotely, and then you have very nice interaction. But if you look at Pepper, Pepper postulates very strong personality by itself. So when you have mobile robotic telepresence implemented in Pepper, so you might be talking to a person in the screen, but you always have Pepper as its own entity, holding that person or sort of safeguarding. And that brings a lot of interesting interaction dynamics, Some people say, oh, it looks like, robot pregnant with human inside. So that makes this particular application very interesting to look at, to look at each of those aspects separately and look at them together, what kind of interaction dynamics it can bring, when it's all in one package, in a single package. So the research question which we try to address, now I do it in a very, rude form, but we can say it like this. So if we can build any possible robot, just any, we take any, science fiction movie and try to implement that robot with no problem. So what is the best assistive robotics for elderly care or for healthcare in general? And I don't think I'm ready to answer this question today. I don't think I will be ready to answer this question in a number of years. And that is because this question is very domain related. So we have to look at many different factors. What is elderly care today? Whom are we talking about? Are we talking about people 65 plus who are, well, traditionally we consider that people 65 plus are elderly. If you look, let's say 20 years back, people 65 plus basically would stay rest of their lives in front of TV and, well, enjoy the rest of their lives in the best way possible. If you look at population 65 plus now, today, you'll find out that this population changed dramatically. Not only that they are physically active, they're also more demanding. They want to have better active life. They want to have more activities than we could think about 20 years ago. And that will keep changing. We cannot say that, oh, you know, this is the demand of the elderly, full stop. That will change. And if you're familiar with software development, right, you have to work with all the way changing requirements all the time. So what kind of functionality of assistive robotics is relevant? And that is going to change, right? If we're talking about functionality. Is it important to look at ease of use of the system? If it is important, then how is it related to functionality? We don't know. Is it important to look at perception? So let's say we provide a person with a personal assistive robot. And it could have different forms, right? So you can take a look at, if you've seen Robot and Frank, right? That could be this kind of humanoid robot, very cute, very nice one. But maybe we can provide a person with PR2, which is a little bit more capable, maybe has a little bit more load, but is it perceived well by a person? Is it perceived well by elderly people? Finally, we can take a look at the aspect of safety and security. Is the technology we are providing safe and secure today? Is that going to be safe and secure tomorrow? And all this bunch of questions, they come in play when we try to answer this question, what is the best assistive robot that we can build? And as I said, I don't have any answer. But what we do have is we have methodology how to approach this problem in the best way. And when we when we try to approach this problem from one side or another, most of the time we try to implement some sort of combination of measurements, some combination of approaches that help us to gain the best knowledge and to answer the most relevant questions. Again, we start with identifying stakeholders. Assistive robotics is a piece of technology. We take the same technological approach that we've been taking for decades in software development and product development. We identify stakeholders. Who are stakeholders of, let's say, robot for elderly care, home robot for elderly care? Obviously, it's a person, it's a local person, right? The one who lives with the robot. That is clear. But other stakeholders, could that be also relatives of that person? Yes, for sure. Is medical institution, support organization part of the stakeholders? Most likely, yes. And then we try to identify all people involved into this process. We try to identify their requirements. We conduct interviews, we do literature studies, and it's a lot of work has been done here locally in different countries, and also on a big European level, trying to identify what are requirements of the whole system. We also do a lot of fielding, and that is basically something that we spend majority of our resources for. Field studies, they take form of short-term evaluations and long-term evaluations. Short-term can be as short as trials that take 10-15 minutes, and long-term it's trials that take up to several years. We had test sites that lasted for 4 years with the same person with the same robot. We combine lab tests with test sites. So we try to, if there is something we can test in the lab, we do that. But very often we need to test in real home environment or real healthcare environment. And we try to combine subjective and objective evaluation. So of course, if you have telepresence robot, we try to see, is it easy to drive it? How many collisions can you make on a simple straight line with no obstacles? And then we have to take a look at other aspects of using technology. Is it easy to use? What is the burden of that use? And finally, last but not least, is that we try, when possible, to have dev loop experimentation. And that means that we try to combine field testing with active development of technology. Usually it happens on the early stage of research project. So methodological approach is the idea. Important part comes when it comes to implementation. And I have a timeline here for the next, for the last 10, a little bit more than 10 years. In our research center, we have a history of projects. I only listed big projects spanning more than several million euros and covering more than 1 or 2 countries. So most of them are European projects. And we started with a project called Excite, that was ambient assisted living project, which basically tried to look at how to use telepresence technology and how to develop telepresence technology so it's useful in the elderly care domain. Then we had a number of projects. We had Robotera and Giraffe Plus that were FP7, and Robotera looked, as I mentioned before, at the ecosystem of several robotic technologies, each of them independent but working as a solid system. And in Giraffe Plus, we looked more at the sensor network aspect. So how can we figure out what are activities of daily living of an elderly person and how communication can be allowed through robotic telepresence. And we do have a number of projects running, spanning for several years. Usually it's 4 or 5 years. Some of them funded by Horizon. Many are funded nowadays by Marie Skłodowska-Curie Action. Examples of those are, for instance, Socrates. It's a European Training Network project where we have 15 PhD students working together and independently on the topics related to healthcare and elderly care domain. And in implementation part, it's important that we focus on the key research aspects, on the key research questions that are relevant to the technology today and will be relevant to that technology in the future. So the question is, what do we actually do? When I joined Örebro University, it was March 2012. I started my postdoc right after graduating. And the first thing I wanted to do is basically to see how easy is it to drive a robot. I mean, you can drive a car, you can drive a bicycle. It doesn't seem to be as a big deal. And at that time, we had a project. It was Excite project, and the robot was called Giraffe. And it was an interesting one. It was the blue one, which I mentioned on one of the first slides. As simple as it possibly can get. You know, just telepresence, so just two-way video, audio communication, differential drive, fully symmetrical, easy to do, and you click on the screen and it drives. There's nothing that can be simpler than that. No autonomy whatsoever, no collision avoidance, no sensors on the robot, just pure driving. And the question which we wanted to look at is usability of driving interface. It's commercially available platform, right? It's not a prototype that we built in a garage. It's a commercial platform. There is a predefined path in the environment. So we took subjects in, we familiarized them with the environment, we showed them, here is where you're going to drive, here is the path, here are the obstacles, what could possibly go wrong? And we applied a number of measures. Of course, we wanted to look at collisions, we wanted to look at speed, how quickly they complete the course. But we also wanted to take a look at their experiences. So we conducted use questionnaire to measure to the best degree possible usability of the interface in the standardized form. And then we applied NASA TLX. So TLX allows you to measure mental workload during some task when you work on the computer. So in some cases, you have to do profiling. What is the characteristic of workload? It could be physical, right? But in many cases, when you deal with such kind of interfaces, you deal with mental capacity that is draining. And then we had 10 subjects, 4 female, 6 male, mean age 40 years with standard deviation 15. And results we came to were, well, basically inconclusive. We're not going to do ANOVA on 10 subjects, right? It's not such a huge sample. But what was important for us to see is the ease of use in general for different subjects. We had some that are, they all different backgrounds. Some are, tech savvy. Some are completely, have complete user perspective, so to speak. None of them familiar with robotic technology. So we wanted to observe, we wanted to talk to them. What do they feel? And in the next slide, I will just show you one of the driving sessions, not the worst one, that we had from one of the subjects. There's no audio, I hope, so I'll keep talking. The interface to the driving interface of this robot is fairly simple. You basically click with your mouse on some part of the screen, and the robot starts driving. There is a line that is showing you approximately the direction where you're going to go. The longer the line, the faster you go. If you bend the line to the left or right, the robot is going to turn. So everything is pretty much straightforward. And you are in full control of what robot is doing at all times. So the first obstacle that we hit in this trial was vacuum cleaner. Used to be quite expensive one. And then basically this subject tried to use speed a little bit and drive a little bit more carefully. And if you've been working practically in robotics for in the past couple of years, you can do it better. You can make robot drive straight if you see that the user is trying to drive straight. In this case, we didn't have any intelligence behind, so it's a little bit clumsy to drive. And in this course, we try to combine line following with some very rudimentary action, like rotate in place. So go to that room, rotate in place, go to another room, go to the kitchen, see what's there. And there is a reason why we took this scenario. The reason is very simple. When so in Sweden, in elderly care domain, we used to have many older adults living independently in their homes. And so of course, no one wants to go to the retirement home. It's not the best place to be, probably. So people want to stay independent. People want to stay in their homes as long as it's possible. And healthcare professionals, they come, nurses, usually they come and visit elderly at some period of time. Usually it happens 1 or 2 times a week. And nurses who work in this service in Örebro, they need to, so they have a schedule, how many people they need to visit during the day. And in that schedule, they have 5 minutes to traverse between different parts of the city. Örebro is not big, but there's no way you do it in 5 minutes. So what we try to do, we try to replicate a procedure that normally nurses would do at home. So they come, they say, hi, how are you doing? They inspect the environment, they see if everything is in order, that the person is doing well, and they leave. So practically, there's no reason for personal visit. You can drive a robot. And in the end, they come, so here at this checkpoint, they come to some goal that is on the fridge. Let's say go to 1, and that means go to checkpoint 1. Subjects knew where it is. It's where they started. So I think it will start moving now. And that was replication of the standard procedure that nurses would do. So what we wanted again to observe, how hard is it or how easy is it for a normal user, non-technical user, non-roboticist, to drive the robot. Takes a little bit of familiarization, but it will come. So I think now the person will rotate. And yes, maybe we can scroll a little bit. So in the end, we expect the person to come to the base station and dock the robot. So that's the end of the visit. Our goal was to look at easiness, as I said, and we tried to look at workload, what people experience. We measured that with NASA TLX. And we also wanted to just talk to people, make some interviews, ask them how easy is it to drive. We asked post hoc questionnaire, and in some cases we tried to look at people behavior during driving. And basically what we found is that even though robotically present device is meant for interaction, in most cases, driving activity means leaves no mental capacity for interaction. So it takes such high toll on your mental workload that you cannot speak to anyone. You're just focusing on driving. And you basically operate the system in sort of 2-mode operation setting. So you're either driving or talking. In most cases, you cannot combine the two. And that was very interesting piece of knowledge that we gained from that experiment that we've taken as granted from the before, that it's easy to develop. I'll scroll a little bit of the slides here. So we tried to play with technology in 2013-14, and that is important to do a little bit of own experimentations, sort of research under the table when we do development. And it's important for one particular thing, because you need to know what is the capacity of your system, technical capacity, how much you can embed into that. So in this particular demo, it's not even the paper. We haven't conducted any experiments. We just wanted to make it running. We implemented gaze tracking of remote users, so the one who drives, and face recognition on the robot side. The interesting thing is that in the system we had, there was no access to robot internally. So everything we did, we had to do on the interface part. And that brings you a lot of trouble. So the the video is already compressed, and it has a lot of artifacts. There's a lot of stuff embedded in the video, which you have to crop. It comes with compression artifacts, and this is year 2013, 14. We didn't have any gaze tracker, so we had to build one ourselves. We didn't have any good interface to OpenCV. So we had OpenCV running separately and figuring out where the faces are, and then we had to do some shared memory tricks to share with Pilot software, because it's written in Java. And I think, so here it's already the newer version that has fancy Nimbus look and feel, if you still remember what was that. And that is a lot of fun to do, but it doesn't give you, it didn't give the full image of what is happening. So our main activity, our main effort is to do long-term studies. And we had a number of projects. Excite is one of them. Jira Plus is another of them, where we do long-term field testing. And long-term means 42 months. We had 21 test sites in Excite project plus 15 test sites in Jira Plus. Test site means it's either real older adult person living independently at home, or it could be some retirement facility. So in Sweden, we had a retirement home where I believe we had 8 people living in the same location, and also, of course, healthcare professionals. And we also combined that with short-term evaluations, where we had about 250 subjects from all user groups, so primary users, elderly people, healthcare professionals, their relatives, and all people involved into this process. And we identified basically 5 big areas of challenges in pan-European development. So our test sites were located in Sweden, Italy, and Spain. Very different countries in terms of culture, the way how we live, but also in terms of technical infrastructure. And on the right side bottom image, you see example of, so on the bottom left, it's a typical Swedish home of one person living, a lot of open space, a lot of space to drive, everything is easy. And on the right side, you see a home of one person living in Italy. It's basically no place to drive. If you have collision avoidance algorithm that is looking for some potential obstacles, you probably will never drive anywhere. So you have to figure out what's going on, and that represents home design, right? It can be different in different countries. We also took a look at Asian countries in a project called Crisis, where it gets a lot more complicated. But it boils down also to technical infrastructure. In Sweden, we used to have fiber network in all houses. In Italy, we found out, so the first surprise for us was that even though we can have fantastic downstream, 100 megabits per second, no problem, our upstream is 1 megabit per second, and that is definitely not enough. Well, we can do some really high compressed video stream, but nothing really more than that. Then the health of the users is deteriorating. It differs from test site to test site. There can be different involvement of users and secondary users. Some users see technology is fun to use and important, but some don't. Some say, oh, it's just something, I can put my jacket on the robot and it's nice to have it. Otherwise, I don't use it. And it's important that test site teams act in a synchronized way. And that is also different between countries in the way how healthcare systems are built. So there are several fundings. We have a paper called 42 months of evolution of mobile and field testing or something. So I have references in the end of this presentation. Some findings that I wanted to list here is that we have been able to see that users who behaved more naturally with the robot had higher degree of acceptance. So those who tried to see the robot as an assistant and just behaved with it naturally basically appreciated it more. We've seen that sliding autonomy, or whatever you call it, adjustable autonomy, adaptive autonomy, is important, but it's quite hard to see in elderly care domain when do you need to adjust the level of autonomy. And we also have seen that factors that let you drive easier actually don't help you in social interaction. And here in the image, I have an example where we try to twist the camera. And if you ever operated a robot with very high field of view camera, something like fisheye, you probably enjoy driving, right? So it's really nice to drive it. You see everything around you. If you try driving with 360 in VR, it's even better. if you're not getting motion sick, but it ruins your social interaction because you start to behave in the way that is absolutely not human-like. You can come to someone, from the side. You perfectly see the person in the corner of your screen, so for you it's not a problem, but for the local person it's really not perceived well. And here comes a bit of contradiction. So what should we do? Should we make it easy to drive, or should we make it better to interact? Or if we're switching, how do we do that? And here in the next slide, I wanted to play it with audios, and I leave you to watch it. It's a video of one of the test sites showing approximately what we've been doing.
Io sono conosciuta come nonna Lea, ma sono Lea Ralli. Ho 94 anni adesso. Vivo a Roma e scrivo. I libri ne ho scritti tantissimi. Sono arrivata a 94 libri e tutti i giorni, oltre che occuparmi di casa, passo sempre al computer perché è un blog sul web che a un certo momento va messo tutti i giorni qualche aggiornamento. È da parecchio che sono stata coinvolta in un progetto molto bello. È la costruzione di un robot salvavita che, messo in una casa di una persona anziana, li può aiutare nel momento del bisogno, se c'è una difficoltà o anche un incidente. Il progetto si chiama Giraffe Plus, però io l'ho chiamato Mr. Robby.
Il progetto Giraffe Plus mira a costruire un sistema integrato che combina un insieme di sensori ambientali e fisiologici con un robot di telepresenza per favorire l'interazione sociale. Per i sensori ambientali abbiamo sensori di movimento, sensori di pressione o occupazione, sensori che indicano l'utilizzo di un elettrodomestico o anche sensori che indicano ad esempio se una finestra o una porta sono aperte o chiuse. Esempi di sensori fisiologici sono misuratori di pressione sanguigna oppure misuratori di livello di ossigeno nel sangue o di glicemia nel sangue.
Questo permette, come dire, una risposta punto per punto di quelle che possono essere le esigenze del paziente stesso.
Buonasera signora Lea, come andiamo?
Ma io sto bene?
Allora, siccome lei è una patita del computer,
dovrebbe fare più attenzione
a livello della colonna vertebrale.
Lo so che mi spiate tutte le mie mosse.
La possibilità che può avere una persona anziana di stare in casa è dovuta anche alle sue capacità cognitive, per cui un monitoraggio costante della sua routine ci permette di capire se c'è qualche defiance di tipo cognitivo.
Ho la mente ancora lucida, perché questa è la cosa essenziale, e seguo questo progetto perché devo valutare e vedere un po' se veramente risponde alle cose per cui è stato creato.
Attualmente stiamo testando il sistema in 6 case reali di persone anziane, in particolare 2 in Italia, 2 in Spagna e 2 in Svezia. Il progetto Giraffe Plus è finanziato dalla Comunità Europea, vede coinvolti diversi paesi e sono coinvolti diversi enti di ricerca, industrie e aziende sanitarie nazionali.
Nonna Lea ha capito perfettamente lo spirito del progetto, è molto collaborativa. Il risultato è che una piccola equipe può controllare una grande moltitudine di persone, quindi questo implica poi anche una ricaduta economica, no, sul sistema sanitario e sociale, che deve essere reso esportabile in quelle associazioni che si occupano di medical care in generale.
Mi dà un conforto, perché tanto i miei figli stanno lontani perché abitano lontano, poi io abito sola per mia iniziativa. Ora che ho questa compagnia del robot mi sento più protetta.
So, yes, it was Giraffe Plus project that was over some years ago. We are still exploring or continuing development of the results that we acquired there. And an interesting fact was that, yes, we could do financial studies, we could do financial estimation to say, oh, this is the amount of money that technology is going to save to Europe or to some particular budget in the country when applied in certain contexts. But there are a number of things that we've been able to see only because of long-term development, only because of long-term deployment on the test side. We've seen people making different benefits of the system. We've seen people who increase social contacts, even though they stay independently at their home, but technology could allow them to contact more with their loved ones, more with their caregivers, and thus provide them better quality of life. So I think the time is approaching the end. I will skip a couple of slides here in the middle. Sorry. As I mentioned, we've been doing a lot of technical development, like autonomy on pilot side. We can scroll in the end, maybe. We've been struggling a lot with developing, on the robotic systems that basically have no API on the robot side. If you're working with ROS, if you've always been working with ROS, it's great luxury. Because a number of years ago, we didn't have ROS, we didn't have any, common sense API to which we could communicate. We had to do everything in a hacky way. We've done a lot of, let me switch the slide. We've done a lot of development on the higher level of the concept. And in our current projects, we achieve also interesting problems of interaction. We take a look at social group interaction. So if we have a robot, socially assistive robot, how can the robot join group interaction? And one of the projects done by our PhD student, Sai Krishna, he's approached this problem in a model-driven way, basically using affirmation theory by Camden. So he tries to identify there are groups in the same individual, and if there are groups, what is formation of people in that group? He tries to identify if there is any spot the robot can join, and it's all done from an egocentric perspective of the camera. So, of course, it's one part of the problem. To see everything from top-down view. And we try to address the problem if we have everything incorporated in one single robot, in one entity, that we don't have a global knowledge about environment, that we only see part of the image from an egocentric perspective. And we've been also doing a lot of work on perceived qualities of the robot. And this work has been done by Miziha Kalin, who is our PhD student in Socrates project. And it was a very interesting comment, very good comment in the morning in Gulen's talk. Sorry for copy-pasting it. It was about robotic arm in that experiment. So someone said, I'll be hesitate whenever the robot arm moves. And that is exactly the problem that we try to investigate. How do you feel when you talk to a robot? And there are different kinds of robots, right? You can use Pepper, or you can use Now, a very small robot in the healthcare domain. Now can do basically anything, practically useful from manipulation perspective, right? So it's no work done, no harm. But you can use your 10 or some stronger robot. It's considered to be compliant. It's considered to be sort of safe because of force control and torque control in every joint. But it still can be perceived as dangerous. And we conducted a set of experiments where we tried to analyze how different motion of the robot can be perceived in the way to be interpreted as safe and secure. And a lot of interesting findings come basically starting from the simple fact that safety and security can have very different meanings in very different contexts. If you think about cybersecurity, or if you're thinking about something else, or physical security and safety, in physical human-robot interaction. And we tried for configurations of the robot moving in experimental evaluation. And we conducted video-based scenario that allows us to, it has its own drawbacks, right? In video-based experiment, you don't have real interaction, but you can have more subjects. So the important result we came up with is evaluation framework, basically questionnaire-based self-assessment evaluation framework that has high internal consistency. It's tested on 160 subjects, and it is viable to assess sense of safety and security in general in HRI scenarios, so we can know if the person feels safe and secure while communicating to one particular robot. So it's all been happening for quite many years already, and one thing that happens, unfortunately, and it happens naturally in the industry, is that Giraffe went bankrupt. The company we worked a lot with, and then it was another company, JoyceCare, which overtook technology, and then there was, now it's Commercialization Care. It's also a Swedish company that basically drives this technology forward. And for us at university, it meant that even though those companies are fantastic in the way in the way they go, in the way they want to collaborate, sometimes it's a little bit out of their capacity to collaborate with universities. It's very hard for SME to dedicate resources for particular research projects. So about that time, we started developing our own platforms. And our idea was very simple. We wanted to have a robot that is designed for us. So we took a little bit of, screwed up software development, mindset, and we wanted to focus on robotic telepresence only. We wanted to have platform open for extension, so everything is sort of a plugging or mixing, whatever you call it. We wanted to have it inheritable, so basically anything that can have wheels and screen and camera can be that kind of telepresence robot. We wanted to have separation between interaction domains, so that if you interact with the robot, you interact with the robot. And we wanted to have zero dependencies. So we tried to approach it in the best possible way. We haven't came up with a smart name, so we came up with the fancy one. And we tried to make sure that this technology can stay open. So we actually put a lot of resources into maneuvering between different patents in the industry. Some companies try to patent the wheel, some companies try to patent suspension in general, and you have to maneuver around that corners so you don't breach anyone's patent. And we've conducted a number of studies. I think I'll skip this one, in which we continued to look at levels of autonomy. And when COVID came, and we had a basically running system, our idea was that, all right, we swap screen to the lamp and go out in the field and disinfect everything. And our idea was to basically make technology available for people to use. If you want to use it in the hospital, great. If you can use it in the changing room in some gym, even better. It's easier environment than hospital environment. And that was basically it. And at some point we figure out that, maybe I will just switch this. We figure out that we have to make a spin-off. And fortunately for us, our university has very elaborated framework how to make spins off. So now we ended up being a very extremely small startup doing robotic telepresence platform that is maybe 20% of hardware and 80% of software, and it provides us as a researchers opportunity to have platform that is sort of vendor agnostic, that can be used in different contexts without being bothered about collaborating with companies that have their own ideas. And it can be free for individuals, open source and modular, everything we love in robotics research and everything that people in commercialization actually don't want to hear. So with that, I think I have nothing more to say. We need to keep to the schedule. Thank you very much for your attention. I think I'll check if there are any questions in the chat. And I can scroll to the next slide. So you can see the references, but I think I can also share my presentation after the event. Right. Question. Do you think that given more time, that more people will be more accepting of assistive robot? The current old generation is not very tech-minded, at least in my country. Will the next generation be more accepting of those kind of systems? I think so, because what we've seen over years is that not only older adults are more tech-savvy. So we had an experiment subject who came and said, "Oh, I know this robot, it's very nice." And this person was basically some executive in the robotics company. And we wanted to have participants not actually exposed to technology. So that was failure for us. Not only they are more people are tech savvy, but also they have higher demands for communication, for social activities. I cannot predict if assistive robots will be sort of the trend, because it's many different technologies in development. Let's say augmented reality, right? So if in 10 years we all have embedded AR in our glasses, then what's the point to have a robot that basically talks to you if you can fool the brain that there is a robot in augmented reality? But yes, I think the acceptance will increase with the years. So let's see. What is the most difficult challenge in telepresence robotics now, in your opinion? I think, well, there are many challenges. One of them will be solved with time. It's technology that, we need better network infrastructure. It's not everywhere that we have good connectivity, but that is less of a problem. The bigger problem, I think, it's utility of telepresence technology when you put it in elderly home. So you cannot come and say, "Oh, why don't you buy a robot that costs you 10,000 euro just to have, Skype on wheels?" And that is the average price of the robot, Or Pepper is even more expensive, but at least it can move something. So I think utility is a big question. What is the added value we bring to other people? What is the problem we help them with? And finding that utility is a difficult challenge, because we either do that on ad hoc basis, or we ask every person, "What do you need? Do you need coat hanger so you can put your jacket on the robot, or do you need whiteboard so you can put on either?" So what is that? So I don't think it's robotic telepresence is by itself enough to be in elderly homes.